Welcome to This Explainer. Today, we're going to meticulously unpack a groundbreaking research paper from May 2026, and it tests exactly how good modern AI is at, well, hacking. The timeline here is absolutely critical. May 2026 marks a massive leap in the capabilities of autonomous AI agents. Look, we hear constantly about how artificial intelligence is getting smarter, how it's writing better code and solving really complex logic problems. But when it comes to the digital infrastructure that secures our data, our communications, and our physical infrastructure, theoretical smarts just aren't the whole story. We really need to know what these rapidly evolving systems can actually execute in the real world when they are left entirely to their own devices.
And that brings us to the chilling question at the heart of our explainer today. Can AI agents turn security vulnerabilities into real attacks? The answer is something every single tech enthusiast and cybersecurity professional needs to hear. You see, the research team behind this paper set out to determine if today's cutting-edge AI models are merely good at finding theoretical bugs or if they can actually weaponize those bugs into actionable threats. Think of it like a bank heist, right? It's the difference between just noticing a side door is left unlocked and actually having the skills to walk through it, navigate the security lasers, crack the vault, and walk away with the valuables. And we aren't just talking about a few stolen passwords here. We are talking about access to highly sensitive corporate data, critical grid infrastructure, and totally private communications.
Okay, let's quickly hit our roadmap for today. We'll cover 1. The AI exploitation threat. 2. Defining the exploitation challenge. 3. Inside the ExploitGym benchmark. 4. Testing real-world security defenses. 5. The shocking AI benchmark results. And finally, 6. The cybersecurity double-edged sword. Let's dive in.
Starting off with Section 1, the AI exploitation threat.
So the researchers emphasize that because these models are advancing so incredibly quickly, we desperately need a scientific way to measure what they can actually do in the wild. I mean, we are moving well past the era where AI is just some chatbot assistant that helps you draft a polite email or debug a simple Python script. We've officially entered an era of autonomous agents capable of complex, multi-step operations. These agents can now write their own scripts, spin up their own virtual environments, and iterate on their own code without any human intervention whatsoever. As the paper points out, without rigorous, standardized evaluation of these specific capabilities, the security industry is essentially flying blind into a completely new paradigm of digital security risks. We urgently need concrete metrics. Now notice the distinction being made here. Finding a vulnerability is really just step 1. It's not the full hack itself. A vulnerability is simply a flaw. It might be a line of code that handles memory incorrectly, leading to a buffer overflow, or maybe a misconfigured permission setting in a cloud bucket. But on its own, a vulnerability is totally passive. To go back to our earlier analogy, it's merely jiggling a doorknob and finding out it isn't fully latched. AI has already proven quite adept at scanning millions of lines of code and spotting these loose doorknobs. But spotting the door is only half the battle. Picking the lock and disabling the alarm on the other side, that is a completely different skill set. Moving right along to Section 2, defining the exploitation challenge. The crucial point here is that exploitation requires an AI to take that initial flaw and aggressively force it into a working breach. This is where the rubber meets the road in cybersecurity. Exploitation is a highly technical process of manipulating a vulnerability to achieve a concrete security impact. This means the AI actually forces the system to do something it was literally never designed to do, like gaining root access, quietly stealing a database of password hashes, or dropping a malicious malware payload that can execute on the target machine. This bridges the massive gap between a theoretical risk on a spreadsheet and a fully compromised hijacked system. To truly understand why this is so remarkably difficult, imagine navigating a shifting maze blindfolded. That is essentially what an AI must do when reasoning about memory layouts. Modern systems use defenses like address space layout randomization, or ASLR, meaning the physical location of data changes every single time a program runs. The maze is literally shifting. An AI can't just memorize a static script. It has to deeply understand registers, calculate exact memory addresses, and manipulate raw hex codes. And if the system responds unexpectedly during the attack, the AI has to adapt on the fly, maintaining a highly specific strategy over a long time horizon to string together multiple smaller exploits into a full system takeover. It's incredibly complex. Because it requires such sustained complex reasoning and deep system-level understanding, the researchers note a massive gap in how we currently test AI safety.
Up until now, we've relied on relatively simple benchmarks, like capture the flag or CTF puzzles, which often just test isolated concepts in very artificial environments. But evaluating an AI's ability to conduct a multi-step, highly technical software exploit against real-world software, that is exponentially harder to simulate and grade. This lack of rigorous, realistic testing is exactly the problem the authors of this paper decided to fix. Which brings us to Section 3, Inside the ExploitGym Benchmark.
Enter ExploitGym. It acts as a rigorous scientific testing ground, giving AI agents a vulnerability and asking them to progressively extend it into a working exploit. Instead of relying on anecdotes or tiny artificial tests, the researchers pulled directly from public CVE databases, the official logs of real-world cybersecurity vulnerabilities. They engineered a comprehensive system where they can drop an AI agent into a secure arena, hand it a known real-world vulnerability, and empirically measure if the AI can successfully execute the attack from start to finish. 898. This massive number brilliantly illustrates the unprecedented scale of their test. They compiled nearly 900 distinct instances sourced from those real-world vulnerabilities. To put this in perspective for you, if you asked a team of elite human security researchers to manually test and write bespoke exploits for 898 unique scenarios, it would take them months, if not years, of dedicated engineering. By operating at this massive scale, the researchers ensured that the ExploitGym benchmark is incredibly robust. It completely prevents an AI model from just getting lucky on a few specific types of bugs, demanding instead a broad, deeply generalizable capability for hacking.
As we look at these 3 target domains, you can see they aren't just testing simple, poorly coded websites here. They are going after the foundational layers of modern computing. They tested the agents against standard user space programs, sure, but they also escalated to Google's V8 JavaScript engine. V8 utilizes complex just-in-time compilation and is scrutinized by top-tier security researchers daily because it powers almost every modern web browser. And incredibly, they even tested the AI against the Linux kernel itself. That is a heavily fortified environment that requires elite-level system architecture comprehension to breach. Exploiting these domains isn't script kiddie work. These are the absolute crown jewels of digital infrastructure.
All right, moving to Section 4, Testing Real-World Security Defenses. The methodology here is highly controlled, ensuring every single attempt is measured objectively in an isolated, containerized environment. First, they trigger the initial flaw, handing the AI the starting point. Then the AI is unleashed to try and extend that flaw into a full exploit. Finally, they use a reproducible container. Think of it as a perfectly sealed, identical digital room for every single test to verify if the attack actually worked. They check for undeniable proof of a breach, like the AI successfully dropping a hidden flag file on the system or establishing an active reverse shell back to the attacker. This is pristine, indisputable computer science methodology.
Crucially, they didn't just leave the virtual doors wide open for the AI. They varied the security protections to see if standard defenses could stop an AI in its tracks. ExploitGym allows researchers to explicitly toggle industry standard defenses like DEP, Data Execution Prevention, which stops malicious code from running in memory, as well as the previously mentioned ASLR and Stack Canaries, which are designed to detect memory corruption. This is brilliant because it lets researchers isolate exactly how much a specific defense hinders the AI, providing invaluable, highly detailed data for security engineers who are trying to build better shields.
So this sets the stage for the climax of the paper, testing the absolute bleeding-edge frontier models against these hardened real-world scenarios. The researchers weren't testing yesterday's open-source hobby projects. They brought in the heavy hitters, the most advanced AI systems available in May 2026. This prompts a massive question. Are these multi-million-dollar AI brains smart enough to outwit decades of hardened cybersecurity protocols when presented with a deeply technical real-world challenge? Let's look at Section 5, the shocking AI benchmark results. Out of the 898 instances, Anthropic's Claude Mythos preview successfully generated 157 working exploits, while OpenAI's GPT 5.5 generated 120. Let's break down that math for a second. 157 out of 898 is roughly a 17% success rate for Claude. Now, while 17% might sound low if you're taking a high school history test, in the world of high-stakes cybersecurity, an autonomous agent successfully breaching your system 17% of the time on its very first try, that is a terrifying success rate. These are AI agents autonomously reasoning through complex memory layouts to produce over 100 fully functional, destructive exploits in a fraction of the time it would take a human. What you should really take away from this is that standard, everyday security patches, they are not a silver bullet against these advanced AI agents. The paper notes that even when they cranked up the security protections, enabling the ASLR and stack canneries widely used across the enterprise sector right now, the models still maintained a non-trivial success rate. There is a tasteful irony here. The complex, hardened security measures that companies spend millions of dollars implementing were viewed by these AIs merely as temporary speed bumps, not impenetrable roadblocks. We absolutely cannot simply rely on legacy security practices anymore.
Finally, Section 6, the cybersecurity double-edged sword.
This brings us to the ultimate dual-use dilemma. The exact same technical reasoning skills that help a security team patch a flaw can be weaponized to exploit it. These AI capabilities are incredible tools for defensive workflows, for sure. An AI that understands memory corruption well enough to write a functional exploit can also be instructed to instantly generate the patch for it, fundamentally accelerating how fast blue teams can respond to novel threats. But simultaneously, this exact same capability dramatically lowers the barrier to entry for offensive attacks, providing malicious actors with an automated, scalable hacking engine that quite literally never sleeps. As the authors conclude, we now have the proof and the testing methodology to show that AI hacking is no longer science fiction. ExploitGym has proven itself as a strictly necessary tool, giving us a standardized way to evaluate the threat. The real breakthrough of ExploitGym isn't just proving that AI can hack. It's giving the security industry a highly accurate ruler to deeply and precisely measure how well they hack, so we can track the evolution of this threat over time. The risk is growing, it is deeply measurable, and thanks to this research, it is finally out in the open. We leave you with that provocative thought to consider the safety of our digital world as these agents grow ever more sophisticated. We've seen today that frontier models can navigate shifting memory layouts, bypass industry-standard defenses, and turn seemingly simple software flaws into critical, system-level breaches completely autonomously. The benchmark has officially been set. Thank you so much for joining me on this deep dive into the ExploitGym paper, and keep seeking to understand the highly complex systems that are rapidly shaping our digital future.